Okay, so we can start. Yeah, amazing. So, good afternoon, everyone. Thanks for being here today, and thank you for this wonderful opportunity to present our work on fuzzy superfluidity. Um, so my talk consists of two parts. The second part is actually about our findings for the Bose-Einstein condensation and superfluidity on a fuzzy sphere. And I know that this workshop is focused on unconventional magnetism and superconductivity, and here we will mostly focus on superfluidity. However, well, anyway, what is a superfluid if not a charge-neutral superconductor? But the unconventional part is aplenty, and it's hidden in the word fuzzy. So the first part of the talk is going to be on the notion of fuzzy spheres and fuzzy manifolds or whatnot, and basically on non-commutative spaces and why we care about them. And just a remark that the previous section was pretty theory heavy, and I think this one is generally more experimental, but I will be a sprinkle of theory in this session. So what do we mean when we say fuzzy sphere, fuzzy whatever? Basically, it means non-commutative. And of course, non-commutativity can have many different interpretations. We, in our work, just from the basis of the quantum mechanics, are familiar with the non-commutativity of the coordinate and momentum operators, on the non-commutativity of the components of the angular momentum operators, and generally in life, when you think just about rotation of three-dimensional objects, these operations are non-commutative. So this is something not completely strange to us. However, what is something that is very useful for us, and like where we live in, is that the space itself is commutative, right? And we're going to change that. But however, we know that for operators, observables, whose operators are not commutative, there exist uncertainty principles, which is true for like momentum coordinate operators and so on. But what does this uncertainty mean, right? Is that there is an uncertainty in the measurement. So there is, one can know precisely one, but not another. And this makes things more interesting. And there is an inherent connection between a non-zero commutator and an uncertainty principle. So we know that in our world, we can have two dots, A and B, 2 points. They're zero-dimensional objects. And if we put a grid, just for better visualization, if we want to go from point A to point B, say we apply one operator Y, operator X, and this is going to be our path 1. And we expect that if we now reverse the operations, but they're going to be the same, first X, then Y, we're going to arrive at the same point by both paths, and those paths are equivalent. And this is something that we are very inherently familiar with. However, the non-commutative space is going to be presented here, mostly deals with things where the space itself is non-commutative, which in turn implies an uncertainty relation between your spatial components, spatial operators, and also means that the notion of a point is more complicated because, like, if you know the position at an X position, then there is a problem with measuring the Y and so on. And so our points A and B turn now into some stranger, more blurry points. And if we do the same trick again, we try to visualize the grid, we apply our coordinates change operators, again, path 1, path 2, oops, because if you go by path 1 or by the path 2, you arrive not to B, but to C in one way or another. And this is directly related to the uncertainty principle. Like, there is a high chance that you'll arrive somewhere else. And this just showcases that the operators now are non-commutative and and the paths are not equivalent. And so what this means for us, for these spaces, is that due to this uncertainty, you introduce a certain coarse grayness to your manifold, to your space where all those points or blurry points live, which now makes them more interesting, more blurry, and less well-defined, which coarse grains the plane itself, and that you have and now this uncertainty. And so basically, if you think about a new space, this non-commutative space, you can think about it as having a new scale for things. So you have this new characteristic length scale for anything that you want to consider there. And this is why people call it fuzzy. This is why it's fuzzy space. We'll see fuzzy sphere. This is basically means that your manifold is non-commutative in this very simple way. And I think that blurry is a better word, to be honest, but I'm like 50 years late to the party to rename it. So now, why care? Why do we even look at something like that? Well, let's look at some non-commutativity in the context of condensed matter and just look something more normal. So a very famous, nice example in the context of introducing non-commutativity is the Landau level problem, or the projection to the lowest Landau level. Imagine that you have a sphere, and in the middle of the sphere you put a monopole, and this creates a radial magnetic field. And then you consider an electron on the surface of the sphere, just like existing. And then if you look at Hamiltonian, which describes this single particle state, it's going to have the following form, where this lambda, this momentum, is given by this. Basically, you can think of it as like connection to the covariant derivative to the usual angular momentum. However, because of the presence of the monopole, you have this additional term in the definition for your angular momentum. So you have a modified algebra of the angular momentum generators. And now if we go to the lowest Landau level, so basically like a static particle on the sphere, you can neglect this the kinetic part of the thing, and then you have an equivalence, or like the proportionality between an angular momentum operator and your coordinates or your space. And this, like, we're familiar with the angular momentum operator having the non-commutative relations between its components, and then because of this relation, you immediately obtain, you can immediately talk about a space where coordinates do not commute, where S is the strength of your monopole. So basically this R over S here, so the radius of your sphere over the strength of the monopole, or anything else that we're going to see here, it's something that we will refer to as the non-commutativity parameter. And this is the central point of everything we'll be doing here. So what's interesting in a more condensed matter form is that we know that there is an equivalence between a quantum mechanical problem of a charged particle even on a plane in the presence of a perpendicular magnetic field, and equivalence to the Chern-Simons gauge field theory. If you think about a charged particle on a plane, it has the following Lagrangian, the kinetic term, and the term which couples to the magnetic field, where, of course, if you are in 2D, your magnetic field is just B, it's not a vector. And now if you look at the Chern-Simons gauge field theory, something that's like strictly like famously connected to the non-trivial topology, and you look at it in the long wavelength limit, so like long range limit, neglecting the spatial derivatives, for example, you get something that looks like this. This is your Chern-Simons term, and this is your Maxwell term. And the cool part that they basically look the same. And here, if you look at if you think about our quantum mechanical problem, lowest Landau level, which in this case just means that the kinetic term goes to zero and mass goes to zero, you obtain a similar non-commutativity relation between the coordinates. Like this is a Landau problem, this is a Landau problem, this is the sphere, this is the plane, but the point is you get non-commutativity anyway, it's just different, and you can generate non-commutativity from different geometries and ways of thinking about things, where here, like the strength, the non-commutativity parameter is connected to your external magnetic field. And then there is this interplay, this connection, this equivalence between this problem and the Chern-Simons gauge field theory. And where, of course, there you can also have your analog of the lowest Landau level and what it means and what non-commutativity means. In this case, it will be non-commutativity for your gauge field I and AG components. And probably this is not super surprising then that if non-commutativity appears for those things, in effective field theories that have Chern-Simons term, that it also appeared in the effective description of the quantum Hall fluids, quantum Hall effect for like fractional statistics in general. So what you can do further, just thinking about this analogy, thinking about how the non-commutativity works, is to try to write matrix Chern-Simons gauge theory, which will capture the behavior of your quantum Hall fluid. So you think of it as a puddle on 2 dimensions, whatever it is, a plane or a sphere, doesn't matter, and you have your like spinless electrons, and you want the system to replicate your fractional quantum Hall behavior. So you want some fractional statistics, you want a Laughlin state, you want something interesting there, and of course, Chern-Simons term itself is strongly related to this coupling between like the magnetic flux and the charge. And what appears here in this theory is that you start with the notion of just charged particles in an electromagnetic field or magnetic field, and you try to go from this mechanical imagination to something more like a fluid mechanics, where now the behavior of the system of this fluid is described by two continuous fields x1 and x2 that you see here, which are actually n by n matrices. And they have a non-commutativity parameter connecting them, which is directly related to the filling fraction and to your magnetic field. And here, if you look, and here you're looking at the fuzzy manifold, basically. And then one can show that the action that would capture this behavior, this Laughlin state of the fractional quantum Hall effect, has the following form, where xy, x1, x2, they kind of look, you can think of them as the spatial components of the gauge field, something that appears here in the Chern-Simons. And what's cool is that if you have this A naught, the zero component of your gauge field, if you now, and you can derive from this action your Gauss law, the analog of Gauss law for this theory, which will immediately produce you the non-commutativity. And this way of thinking about things introduces non-commutativity again and again in different forms, not only the projection to the lowest Landau level or this effective description of quantum Hall fluids, but also there is a connection to integrable systems such as the Caldera-Sutherland model. And then if you have an integrable system, wow, immediately you can do so many different things. And it is connected to non-commutativity. Also, it's quite useful in describing collective excitations of vortex lattices in rotating superfluids, the so-called Tkachenko oscillation mode. So like we know that if you have a bucket of helium-4 and you freeze it and start rotating it, eventually you'll obtain a lattice of vortices forming in there. And effective description of these collective excitations can be described by a similar matrix gauge theory that is non-commutative. And for us, it was also interesting as maybe a future prospect. So around a year ago, we looked into effective field theory for wire superconductors. And there, what you see again and again is this coupling between electric and magnetic field introduced by the topology of the system, which in turn means that if you think about the vortex solutions in such superconductors, they are the vortices are charged, and which is like cool and interesting, and and therefore they have a non-zero angular momentum, and as we've seen, angular momentum is well connected to all the non-commutativity discussion. So maybe this application of non-commutative field theories is also useful in our wire superconductor systems. And of course, as very often is with those effective field theoretical descriptions and for condensed matter systems, everything comes from like string theory or high energy or something. So originally this fuzzy sphere or fuzzy spaces overall were considered as a tool for regularization to study critical phenomena in 2 dimensions. Why? Because fuzzy or non-commutative means that you introduce a new length scale. Yeah, so the point is that fuzziness non-commutativity introduces a new scale for you, which is very important for all the RG flows, all your renormalization group description of phase transitions. So now more about what we were working on, what we are interested in. Well, we know. One second. We know here what a Bose-Einstein condensate is and what superfluidity is, but just a short reminder just to move from all the fuzzy discussion into something more normal. So we know that if we look at the system for Bose gas, ideal or interacting, we can have this macroscopic state at the ground state where bosons condense and act as something more collective excitation. And these Bose-Einstein condensates have cool properties that were actually measured in different experimental scenarios, and we know that the Bose-Einstein condensation is strongly connected to the notion of superfluidity. And we know the superfluid is a fluid that below some temperature starts flowing without any viscosity and has many other interesting properties. And in principle, to describe this interacting Bose gas, we can have the following action where this psi is an order parameter for the superfluid. This is your chemical potential. This is the term, the phi-4, which corresponds to interaction. Basically, a non-relativistic phi-4 theory is what you're looking at. The crucial part here is that Bose-Einstein condensation is not the same as superfluidity. You can have superfluidity without the Bose-Einstein condensation, and even if you are at a zero temperature superfluid, all your density of the fluid is superfluid. You can still have like a 13% fraction of actual condensate there, and we know that this behavior, this phase transition to the condensate or to superfluidity, is of course very dependent on dimensionality. So we know that because of the Mermin-Wagner theorem, there is no Bose-Einstein condensation in 2 dimensions, but still you can have superfluidity, which is governed by the transition governed by the BKT transition. However, if you look at more interesting, like not a 2-dimensional plane, but some other manifold, a compact manifold like a sphere, which is still 2-dimensional, then everything is possible. You can have both Bose-Einstein condensation and superfluidity, and basically this is the model that we now want to put on a fuzzy non-commutative sphere. Sphere because we want something compact, we want for Bose-Einstein condensation to occur, and fuzzy because we are interested in the way this additional uncertainty, which can be introduced in many different ways to the system, actually changes and alters our behavior of our Bose-Einstein condensate and of our superfluidity. So the system that we are actually working has the following relation between the coordinates and the angular momentum, which is I see 2 angular momentum operator matrices in n-dimensional representation. So your coordinate is a matrix by n by n, and your angular momentum is also a matrix n by n. And of course, because we have this non-commutativity condition, this Lie algebra, the same is true for your coordinates. And so this is what we will be working with, where r is the radius of the vortex, and n is something that we are going to discuss in a minute, like what's the actual meaning behind that. And now a short intro, how do you work with such theory? How do you actually fuzzify something? First, you have to understand what do you do with the partial derivatives, what do you do with your integrals over your sphere, because the coordinates are not exactly smooth anymore, everything is blurry. So the answer to that is that you replace your partial derivatives by the commutator with the operator. This is like a Lie derivative, basically a generator of your rotation now acts as a derivative. And then maybe this is more intuitive, that because you have something that is not super smooth, you have to replace the integral by a trace. And the most important part is that now, instead of dealing with some fields, the functions, like now here, the superfluid order parameter is just a bosonic field, it's just a complex field, right? When you move to the fuzzy description, all your fields become matrices. And that's why this is a trace over this matrix. This is a matrix of n by n dimension. And like this matrix theory really helps you capture non-commutativity. So now this is the action that we saw, this is the system that we saw, our non-relativistic phi-4. We put it now on a fuzzy lattice. This quadratic part, because the time is still is still good. Time is still okay. We don't touch anything there. Don't try to falsify anything there. This part remains the same. However, and because now psi fields are the matrices, of course, the 5-4 term now looks like this. And the most interesting and immediately noticeable change happens in your kinetic term, in your Laplace operator, because now you have to replace it as was anticipated. You have to replace the Laplace operator by two commutators with your rotation generators. And it's fine just from the dimensionality of things that this is supposed to be like k square, right? This is supposed to be a momentum square thing. And you have this 1 over r square, but now the scale, this dimensionality is given by the radius of your sphere. And why this is okay. And now, of course, psi is a complex scalar n by n matrix field. You can play with the trace, something like a partial integration, basically, to really show that this is a square of the angular momentum operator. And this is a wonderful thing for us, because then it makes everything much, much simpler. So now to deal with the system, to find its properties, like what's the temperature of the Bose-Einstein condensation, what's the depletion of our Bose-Einstein condensate, what's the superfluid density, all of those are spoilers for the future slides. It's nice to use this expansion for our psi field, where TLM are the matrices corresponding to this n-dimensional representation of SU2 algebra. And these are just nice complex fields that we love to work with. This is not a matrix. And this T you can think of as a matrix. This is your basis. This is coming from your SU2 representation. So they are orthonormal, which is very good. And now you have here the expansion, which corresponds to like those quantum numbers that correspond to the magnetic quantum number and azimuthal quantum number, basically something that is coming from your angular momentum. And the crucial difference here from like from describing Bose-Einstein condensate Bose gas on a commutative sphere, the normal sphere, and what we do here is the fact that you have this upper cutoff on the values of your angular momentum. You can think of it as really a discretization of your levels, and the fuzziness introduces a natural upper cutoff on what would be your momentum. And this is very interesting because first, of course, this is something relevant for all the RG behavior, like you have a natural a cutoff there for your momentum. Second is how do you actually interpret that? Where does it come from? And what our attention will be on in a couple of next slides is how all those properties of Bose gas I mentioned actually depend on this M, which I will be referring from now on as the non-commutativity parameter, because this is the thing that defines non-commutativity. If M goes to infinity, this is your commutative limit. You are now in a normal sphere. Okay. So first thing you can do is calculate the ideal, like look at the ideal Bose gas. There is no interaction. This epsilon L as just what your kinetic term would be. It's like k squared over 2. Of course, using this action, you can calculate the partition function, find the particle density, the condensate density, and see what's the actual temperature of the Bose-Einstein condensation here. And what we are actually interested in is this dependence on M here. Dependence on our non-commutativity parameter. You can see this on this plot. Basically, this is a function of our Bose-Einstein condensation temperature for different values of their radius. And we know that if R goes to infinity, your temperature should go to 0 because this is no Bose condensate on the plane. And this is for different values of your non-commutativity parameter. And what you actually see here is that the stronger the non-commutativity, the stronger the discreteness of space, this coarse grayness, the higher the temperature of the Bose-Einstein condensation. So basically, this discreteness helps you condensate. And we find it also for an interacting Bose gas. This is a little bit more complicated, but you just do the Bogoliubov approximation, say, okay, something with L equals 0 is my condensate, everything else is my fluctuation, and I only want an action that is quadratic in my fluctuations. I then go look at the action, integrate out my fluctuations, obtain the partition function, and then from the partition function, I can calculate the free energy density, from it the particle density, and then we find the Bogoliubov spectrum for this superfluid thing on a sphere, which is very similar to what you would expect in a commutative case. But now here you have this discreteness, these levels that come from your fuzziness, from your sphere. And then if you look at the actual particle density, you find the condensate depletion. Condensate depletion is something that occurs also in a completely normal superfluid, but basically what it means is that even at zero temperature, even if you go to zero temperature, because of the interactions, not everything is condensate. And you can see here the dependence of this overall, this is temperature independent and temperature dependent parts of our condensate depletion as a function of R, of the radius of our sphere, for different values of fuzziness. And again, what you see is that the stronger the fuzziness, the stronger the non-commutativity, the smaller the depletion of your condensate, which is very nice if you want to keep your condensate, something that helps the stability of the condensate again and again. And of course, you can also see at zero temperature, there's this expression. And now what we were looking at is the superfluidity. You can also calculate the superfluid density. So that was particle density, now we want the superfluid. And again, you can have superfluid without the Bose-Einstein condensation. It's like two different things. And how you find the superfluid density is by doing the Galilei boost and knowing that the superfluid part of your fluid, of your two-fluid picture, is going to be not Galilei boost invariant. You can calculate that and express your superfluid density through your normal density. You have this nice long expression that we're not going to talk about, I guess, but it is depicted here, and this is the main point, that again, the larger the non-commutativity, the smaller the rho normal, which means that more of your fluid overall is in the superfluid state. And what's more interesting is, maybe like more intuitive, is that if you look at large R limit for finite M, so you have fuzziness, but your sphere is large, and look at the expression for the normal fluid density, you have a behavior that is linear in temperature, as opposed to a commutative limit, where this normal fluid will be cubic in temperature, which in some way invokes, for some people, the Euler's law, where for high TC cuprate superconductors, you have a very similar linear in T behavior for linear behavior for your superfluid density. With this, I would like to move to conclusions. I'm just going to keep them there. The point is, more fuzzy is better. Why is a very interesting question, and thank you for your attention.
I have a couple of questions, but maybe a couple of first here from the audience. Yeah. Sergey?
My question is, what is the practical realization?
Yeah, it was. So, yeah, okay. So there are a couple of things which I think are interesting. One is that actually, if you look in one of their first original papers on experimental realization of the BKT transition, like from the 70s, they measure a film of a superfluid on an oscillating substrate. It's a plane, of course, and you have this oscillation with some given external frequency. And I think that basically what we think about fuzzy sphere is that it's a sphere covered, like it's a surface of a sphere covered in a thin superfluid film. And if you just shake it, this external frequency introduces an additional cut, like basically like a natural cutoff to your angular momentum values. And I think that you can interpret just the physical cutoff on the angular momentum as a feature of fuzziness. So you can reinterpret those things as like you can reinterpret a system like that from a point of view of fuzzy coordinates. Or this is one thing, but then also like for just spherical things, the experiments they do like in microgravity things, they look at like bubble traps somewhere in space for the rubidium atom, like Bose gas systems, where they measure those Bose-Einstein condensation properties and so on. And for them, the sphere is important. The fact that it's composite is important. So like you just have to find a way to shake that.
Okay, I will actually ask a couple of questions. So you mentioned the Mermin-Wagner theorem. That's number one. What happens to the Mermin-Wagner theorem in this case?
It's completely fine because okay, so two ways to answer your question. From our point of view, the fact that you are on a compact manifold, you can still think, like, you can choose to think about the Mermin-Wagner theorem, that it works as it works in commutative spaces, and that the fact that you are compactified the space should allow you already to have this Bose-Einstein condensation. And our thing works perfectly. If you now send it to a plane, even though it's non-commutative, it will replicate no Bose-Einstein condensation, and very conventional, usual row normal behavior. Because I think here, especially with the Bose-Einstein condensation discussion, the fact that you're on compact manifold comes first. You cannot just now send. You cannot go to the plane and keep it fuzzy, because the way we introduce non-commutativity is you have the relation, the ratio between the radius of the sphere and the non-commutativity parameter m. So you cannot do the reverse. You cannot undo things. But I think that the second part is that it can actually have very deep implications if you try to think about the Mermin-Wagner theorem itself in a non-commutative space for non-commutative field theory. And this is something I'm afraid to touch, but maybe it's interesting because maybe it does.
And what about superconductivity? It will also charge up these fields.
Yes. So this is in my outlook, because of course, the natural thing to do is, if you can analyze superfluidity, you now want to charge it and couple to electromagnetic fields and see what happens. The problem with that approach, which we want to do, is that the moment you couple it to the vector gauge field, to the electromagnetic field, everything becomes much more complicated, because the gauge field itself becomes a matrix gauge field, and you have to account for all of those things. But I think this is something that we can look into the future. Yep.
So very sophisticated stuff. but I have a question. So the finite end, can I also think of that as a kind of regularization, or you put things on the letters, right? And
yes.
It's a finite system.
Yes.
So what Asle was saying, that now you're thinking about Mermin-Wagner, but Mermin-Wagner does not really apply on a finite system. Conversely, I can also think that, you're looking at some length scale that is, you're confining. If you would ask question about superconductivity, you would want to go to the thermodynamic limit, and you would actually go to the continuum. So you're kind of restricting yourself to certain length scales, and on that length scale, you still have something that looks like superconductivity. But the question is it really defined? Because if I have a finite system, can I define finite system superconductor?
Okay, so I think we kind of still treating this pretty naively. We kind of do also the thermodynamic limit, because we use all those things you do when you think about Bose-Einstein condensate. And we just think about our volume or whatnot is area, which is just an area of the sphere. So you have this, what does it mean to go into the thermodynamic limit is you have again the interplay between this upper cutoff on your momentum and the radius. And I think so far we've treated it pretty naively. I think if I try to really I had to think about that.
I'm over.
Yeah, exactly. Exactly. Yes.
Not like a reduce the dimensional reduction.
Yeah, so you can think about introducing non-commutativity as also just looking at the Bose gas in a trap, which then also changes the critical dimension for your transition.
With the trap strength is 1/r or something like this?
Yeah. There is a harmonic trap, for example, that you want pass from this, the normal terms for t equals 1, not b equals 2, for example.
Excellent. So I think we have time for one more question, short one, and a short answer.
Why sphere?
Okay, so because it's harder. Yes. Sphere is the easiest way for introducing this something that is compact and non-commutative. Just because you can think about this lowest lambda level situation with a monopole, it's already there. You can think about that, but torus is more complicated.
Torus is a product.
Yeah, why would you? Yeah.
On that happy note, let's thank you, Vira, again. The next speaker is Jörg Fink, also from IFW. and he will talk about 1 and 2 particle spectroscopies and strange metals.
Okay. Good afternoon. First of all, I would like to thank the principal organizer of this workshop to allow me to present our recent results. And I am contrasting 1 and 2 particle spectroscopies in strange metal. And mainly I will talk about acoustic and optical plasmon excitations in cuprates and in rugenates. So these are the collaborators. At the beginning, I will talk about a re-evaluation of our very early plasmon excitation measurements in cuprates. This was done in Karlsruhe, and then I moved to Dresden, and there we now continue to do similar measurements on a tri-layer system. The earlier measurements were on a bilayer systems, and we moved to rugenates, and I had also a collaboration with Rick's group from Diamond, with some collaboration with theories from Argentina. So this is a motivation of our work. So these strange metals which occur at optimal doping of cuprates, they show a resistivity which is linear as a function of temperature over a very large range from millikelvins to 1000 kelvins. And this is one of the great puzzles in solid-state physics. There is a phenomenological theory called marginal Fermi liquid, which is based on a continuum of excitations. There is a holographic theory on plasmons from the Jan Sahnen's group, and they postulated that the plasmons shouldn't exist. They should be overdamped in these strange metals. There are conflicting experimental results between transmission yields, and yields means inelastic electron scattering, and reflection yields. So we see in transmission mainly plasmons below the continuum of the Lindhardt continuum, and they see more continuum, at least at rather small momentum. So the other question is, are these the plasmon dispersion? I will explain this soon. Is it renormalized by high effective mass? And the other question is, the width of the plasmon is under discussion since half a century, since Kivelson proposed that there shouldn't be any plasmon damping because there is no continuum into which plasmons can decay. And the other extreme would be that the plasmons would be overdamped. And finally, I will come to the question, can the 2-particle spectroscopy, which is EELS or optic or Raman, can be related to 1-particle spectroscopy such as ARPAS? If this could be done, could be related, then the scattering rate of ARPAS, twice the scattering of ARPAS should be equal to the scattering rate of the 2-particle spectroscopy, because you have a convolution of 2 Lorentzians in the spectral function. So here I introduce plasmons. So plasmons occur when you shift the electron liquid, for example, to the right. Then you have a surface charge, a negative surface charge on the right, and you have a positive charge of ions on the left. And then you have a restoring force, and this gives you plasmon oscillations, and they have a gap. So this is shown on this side. It starts, for example, at 1 eV, and then you can do excitations at shorter wavelengths, higher momentum, and then you have to compress the electron liquids, and this needs energy, and therefore you see a dispersion of the plasmon to higher energies. But then when this plasmon dispersion merges into the Linhart continuum of single particle excitation, it decays into single particle excitations. Now the plasmon energy is determined in some way by the density of the electronic density, and the dispersion coefficient is determined by the Fermi velocity squared over and averaged over the Brignoles zone. And so you can get, when you measure the dispersion, you can get information on the average Fermi velocity, and this depends on the effective mass. So you can get information on the renormalization of the band structure. Now things may, in some cases, are even more complicated, because you not only have here the optical plasmons at high energy, which are gapped. When you have layered systems, then when you have a momentum perpendicular to the layers, you can get anti-phase oscillation, and when you have a movement to the right and the left, then you need no energy, and therefore the plasmon energy goes to zero, so you have acoustic plasmons. And in both cases, in the homogeneous systems or in the layered system, you can get information from the dispersion on the Fermi velocity, and then you can get information on the renormalization due to a higher effective mass. Now, on the left side, I show you our early data on the plasmon dispersion in BISCO, in bilayered system BISCO. And you see a quadratic dispersion, and we see a well-pronounced plasmon below the point, the critical wave vector, where the plasmon moves into the continuum. This is roughly at about 0.5 angstrom to -1. And this is contrasted with reflection yields from the Urbana group, and they see at lower momentums, they interpret these data by a plasmon excitation below 1/10 of the critical wave vector, and then above, at higher momentum, they believe they see a continuum. So they support, at least at higher momentums, this idea that the plasmon should be overdamped. Now here I show these data again with a new evaluation in terms of a true de Lorentz model. So the first excitation is a plasmon, and then we have interband transition, and we look at the dispersion, and the dispersion is shown here by these black dots. And when we do an RPA calculation with an effective mass of 1, then we get rather good agreement. But when we do the same calculation with an effective mass of 2, which we get, for example, from ARPAS, we see a strong renormalization. So this indicates that the plasmon dispersion is not renormalized by correlation effects. And here we see the dispersion, and the plasmons are as the dispersion of the widths, and we see well-pronounced plasmons up to about 0.5 angstrom to -1, close to this critical wave vector where the plasmon dispersion merges into the Linhart continuum. Now, another important point is that we see an anisotropy of the plasmon dispersion. And if you would assume that we have just an incoherent Fermi liquid, then we shouldn't see any anisotropy. but here we see this anisotropy, which means the dispersion is also determined by the ions, by the interaction with the ions, and this means the dispersion is not determined by an incoherent electron liquid. And one can, when we look at this band structure, then you see along different directions, you have different Fermi velocities, and that's the reason why we see this dispersion. Now, these are recent data on a tri-layer system, and again, we see well-pronounced plasmons, but we see also some discontinuity at momentum which is below this Lindhardt critical wave vector. And also in the width, we see the right panel, we see some discontinuity. And at present, we don't know exactly what it's coming from. But there are two explanations. One is that in the tri-layer system, you have different doping. The outer layers are strongly overdoped, and the inner layer is underdoped. So maybe in the underdoped systems, correlations effects are important. The other explanation would be that within the tri-layer system, you may have anti-phase oscillation, which could also change the dispersion at higher momentum. Yeah, this is just what I have discussed. And now I will come to the connection of the two-particle spectroscopy with the one-particle spectroscopy. So in ARPAS, you see the spectral function, which is given by the imaginary part of the Green's function. And when you go, there are proposals to express the susceptibility of two-particle excitations by a convolution of two Green's function, of two spectral functions. And then you have a convolution of two Lorentzians. So you would expect that maybe the scattering rates in the two-particle spectroscopy would be just twice the scattering rate in the one-particle spectroscopy. And when you calculate then the susceptibility, you can do RPA, and from this you can calculate the loss function, which is the imaginary part of the susceptibility. Now, when you take yields data, for example, those from Sasha or from Adam Kaminsky, then you see at low energy, you see a linear increase of the scattering rate, which also determines the strange metal behavior in the conductivity. But at higher energy, above at about 0.4 eV, it saturates. When you take this imaginary part of the self-energy and calculate the real part, then you get this green curve here, where you have at zero energy, you have a divergent effective mass, but when you go to high energy, then you get an effective mass of 1. When you calculate the spectral function as a function of momentum, then you see you have a renormalization of the band at low energy compared to the bare particle band, which is shown here as a dashed line. But then when you go above this saturation point at 0.4 eV, then the dispersion, the renormalized dispersion goes back and approaches again at high energy the bare particle band structure. This means you have again the effective mass of 1. So at high energy, you have a nearly free electron behavior, but at low energy, you have this renormalization. Now I come to Riggs data, and we have measured these Riggs data on p-type and n-type doped cuprates, and you see a nice dispersion of these acoustic plasmons. And when you look at the plasmon dispersions, then you see a linear increase, which is expected for these acoustic plasmons, and you see a steeper plasmon dispersion for the n-type doped system compared to the p-type doped system. And we can easily explain this because the Fermi velocity in the n-type doped system is higher compared to the p-type doped system, because the p-type doped system is just half filled. So for half filling, we would have a smaller average Fermi velocity, and when you now fill the band structure, then you come to a point where there is a higher average Fermi velocity. This is shown in these two graphs here. And then when you go here to the width as a function of energy, then we see width which can be explained by twice of the single particle self-energy. But for the n-type dope system, we see a reduced increase of the width as a function of energy. And this may be again related to the filling of the band structure, because if you have a complete more and more filled band, then the transition into unoccupied states is reduced, and therefore the scattering rate is reduced as a function of momentum. Now this summarizes in some way our data. So we see for the optic plasmons, this is the lower line, we see roughly when we take twice the self-energy measured by ARPAS, we get to 1.1 eV. When we look at the width measured by Riggs at lower energies, then we get 0.6. And this roughly agrees with twice self-energy measured by ARPAS, but so in the optical spectroscopy, this measured scattering rate is a little bit higher than expected from twice the ARPAS scattering rate. In the acoustic plasmons, we see that the slope is roughly equal to that which is expected from ARPAS, but it's used for n-type doped system. But for p-type doped system, it's close to our expectation. So then I'm coming shortly to the routenates, and in routenates we have cut the single crystals perpendicular to the layers with ion milling. That's not quite easy. And then we can measure with the momentum transfer perpendicular to the layers. And then you see here that the plasmon, for example, with increasing Q perp is reduced more and more in energy. And this is expected because we now move from the optical plasmon to the acoustic plasmons. And this is a summary of our routenate data. We see here the optical plasmon, and then with increasing Q perp, the plasmon moves lower and lower in energy, and we see acoustic plasmon, and this is compared with the continuum of single particle excitation. And this is the width as a function of the momentum, and we see at the critical wave vector at this point here, the plasmon width diverges because the plasmon dispersion moves into this continuum, which is shown here in black. And this on the right side is a comparison with RPA calculation for different effective mass. And we see that for the effective mass of 1, we get good agreement, or for an effective match which is high at low energy but decreases to 1 at high energy, we get good agreement. But when we take for the whole energy range an effective mass of 4, which is measured by ARPIS, then we have less agreement. So this is then the summary. So for the optical plasmons, we see plasmon at an energy of 1 eV or 1.5 eV for the routenates. We see quadratic coherent plasmon dispersion, which decays when we move with the plasmon dispersion into the continuum. We see no overdamped plasmons below this continuum, this Lindhardt continuum. So there, from our side, there is no need for holographic theories which predict this, which predict overdoped plasmons. And the dispersion coefficients can be well explained by an unrenormalized band structure using an RPA approximation. And the explanation of the mass can be only explained below 0.4 eV, because there we have a renormalized band structure, probably due to a coupling to spin fluctuation, but at higher energy, the optical plasmons are not renormalized because the effective mass is at close to 1. And the width is roughly twice the scattering rate measured in yields, which is the same as in optical spectroscopy. It's roughly a factor of 2 of the ARPIS scattering rate. So this relates in some ways a 2-particle spectroscopy with a 1-particle spectroscopy. And at lower energy, the RIX acoustic, we see acoustic plasmons below 0.4 eV for N and P-type dope cuprates, and also for the routenate. And at low energy, the plasmon dispersion is renormalized because there we have high effective mass. And the width of the plasmon in all cases is roughly a factor of 2, or the scattering rate is roughly a factor of 2 bigger than that of single particle excitations. And this indicates that the plasmon width in these correlated systems is mainly determined by correlation effects, but in simple metals like sodium or aluminum, the plasmon width is determined by a decay of interband transition, which is backfolded, but these widths are roughly a factor of 20 smaller than those in the correlated system. So thank you for your attention.
Thank you for a nice talk, and thank you for contributing to bringing us back on schedule here. Are there any questions? Yeah. So, microphone? Yeah.
Why factor of 2 is, you mean empirical? Because so you should integrate this, you should do correlations in this, let's say, between initial state and final state. But you, and each time it is correlation, right? But you should integrate it in this energy, for this, let's say, energy thing.
Yeah.
And but so you start from nearly delta function at Fermi level with some with some energy at an occupied state, and it will be a single. So it's not double. It will be single. then you the same. If you're in the middle, it is also single. So I would expect it will be single, but you say it's 2 times, then it is empirical factor.
Yeah, our plasmons are at 1 eV and above 0.4 eV in APES, for example, you have a constant scattering rate. And when you convolute the occupied state with the unoccupied state, then you get convolution of 2 Lorentzian, which is twice the width of one correlate.
If you consider it constant, but it is, it is very sharp, goes up.
No, of course, we take the full. Yeah, these are calculations from the last week, but we see that when we take the full energy-dependent self-energy and take this energy-dependent self-energy into the Green's functions, then we see at 1 eV we have mainly excitations above 0.4 eV, so this would support twice the self-scattering rate of APES.
Thanks. So I have 2 questions. So one is, could you go actually to the this nice table which compares APES and Eve's lifetimes of widths?
Yeah.
Yeah, this one, yeah. So there's this formula gamma APES to the sigma, yeah? So this is universal, at least for it works, yeah, but with some here, yeah?
Yeah, this is
kind of.
Yeah, this is standard in APES that the scattering rate is twice multiplied by the
sigma from APES.
Yeah.
Then this gamma APES you compare to gamma E's, and conclusion is that it's roughly similar, yeah? That it all works for all of these cube plates.
The second line shows there at low energy we take a Z of 0.5. So the scattering rate is equal to the self-energy, but for higher energy, Z is equal to 1, which means it should be twice sigma.
And it all roughly agrees, basically, yeah?
Yeah, not exactly, but at least qualitatively.
And so this is for qualitatively for all the cube rates of interest for you. But for the Ruffenens, was it similar? If you were to do this?
We haven't done such calculations for the routenates.
Okay, good. And I'm sorry, a short second question in my mind. So
Yeah.
So like some time ago, there was this kind of puzzle or discussion in the RIX community that one can see plasmons on some cube plates in RIX, but not always. Yeah. So is it still like this, or can you comment on this? What's your feeling?
I have looked, for example, through the optical data. And there's a large scattering in the memory function or in the scattering rates, but in total, at least in the average, there's not so much deviation. And the same holds for the APES data. For example, the saturation is also different between occurs at 0.4 eV and ours was 0.9 eV also.
Okay, maybe that's fill up later. Yeah.
Okay. So let's thank Jörg again for a nice talk. And the final talk of the session will be given by Volodymyr Bezguba. Okay. So we'll talk about possible topological superconductivity in iron pnictides. Do you know how to handle this?
I will try. Hopefully it will work.
So I'll give you a 5-minute warning. Okay? After 25.
Yeah. Good afternoon, everyone. It's a pleasure to be here and to see so many people here, both from Ukraine and from abroad, and especially in these times of full-scale war. So I'm very grateful to everyone who came today. And today we'll talk about the search for topological superconductivity in iron-based superconductors. So first of all, why topological superconductivity? It's one of the central topics currently in solid-state physics. due to possible applications for fault-tolerant quantum computing, and because topological superconductors, they carry Majorana fermions, Majorana zero modes, which can be used for as the building blocks for realization of quantum qubits with longer decoherence times. And there are two main ways to realize those. I won't stop too much on that, but one of them is heterostructures, which is shown on the slide above. So this example above is from the Microsoft team, which was very loud in the news last year with their Majorana one. It's a heterostructure. Usually they use something like superconductor semiconductor interface or some other variations of it, and this is like designing the device of sorts. The other approach, which I will cover here, is intrinsic properties of the material. It's much more interesting and better, in my opinion, because you don't have any interface issues, you don't have complications with producing it. It's like if you synthesize this material, it's the property of the material, but of course, the question arises to find such material. And recently, iron-based superconductors were suggested as a platform for topological superconductivity. On the left, you can see the typical families of IBS, their crystal structure. These are layered structures. And on the right, you can see that their band structure is quite complicated. Maybe not as complicated as platinum bismuth 2, but still multi-band system with many bands crossing the Fermi layer. In 2014, it was shown for the first time that actually the spin orbit induced hybridization of pnictogen and pnictogen or chalcogen P bands and iron D bands. They opened the gap, and this gap later, quite fast after that, in 2015, it was shown that this gap is expected to be inverted, which means that the surface states that emerge in it, they are surface states. So this logically brought a lot of attention to this class of materials. And one of the ways how you can check that and how people do that is to do scanning tunneling microscopy to search for Majorana, to search for zero bias peaks, which are signatures of Majorana zero modes, but they are usually they can be strongly intertwined with other peaks coming like from CDGM, and it's tricky. So the better way to do it, or rather to complement that, is of course ARPAS. I won't stop too much on that. Sergey Sharapov earlier today gave a great talk on that and covered the technique in great detail. So I'll just move to one of the materials on which there were a lot of inconsistencies and controversies. Iron, tellurium, selenium with 55% of tellurium and 45% of selenium. There were multiple works showing a bit contradicting results, but the main issue with it was the energy scale and correct interpretation of data, because it's quite tricky again, even though it happens along gamma z cut in brilliant zone, which shouldn't be, which as have been mentioned before, it is not deformed much by ARPAS when you go far away from the center of the angular momentum. You still you get it almost ideal as it is, but interpretation was quite different, and in calculations the inverted gap was expected to be around 5 millieV for inverted gap, but of course iron-based superconductors, they are strongly correlated, and you need to take into account the renormalization. And after normalization and after carefully comparing synchrotron measurements to the theory, we found out that the size of this gap can't be larger than 1 millieV, and in general our interpretation of the results was that this is superconductor with trivial electronic structure. There are no surface states. It has two Dirac points, one above Fermi level, one below, of different types, but unfortunately there were no surface states, or at least we couldn't distinguish them, again because due to strong renormalization, the inverted gap is becoming very, very small. And this brings us to next material, lithium iron arsenide, where from theory we know that inverted gap is several times bigger. So it's already a good idea to check it, because at the very least it should be the same story, and there are more potential for surface states emerging there. But because everyone is already tired, I'll maybe use some crude joke to wake everyone up. It's very important to take into consideration the interplay of topology and superconductivity there, and I will make an analogy with yesterday's nice evening. Like when we were all inside, superconductivity is strong, music is loud, it's hard to communicate. People usually can talk to each other only close by, not across the whole table. And vice versa, when it's outside and you look somewhere on the horizon, there are no people, there is nothing, silence, it's calm, and vice versa. There is no superconductivity, there is nothing happening much. So the perfect case is when you are somewhere in between. You still hear the music, there is still superconductivity, there is still topology in terms of people are talking with each other, and now they can talk in larger group. So this is just a joke comparison, which I'll now elaborate more on the example of lithium iron arsenide. So again, same as with iron tolerant selenium, there were some studies which were showing topological surface states. At the same time, in pristine life as STM showed that there are no MZM in it, so there are no topological surface states. And why is that? We tried to figure it out, and we started from careful study of and comparison of, again, synchrotron ARPAs to the DFT calculations. And first of all, we wanted to figure out what is the renormalization, what is the scale of these important factors which shape the inverted gap and from where the surface states should arise. From this comparison, we found out that renormalization was actually different for different orbitals. So PZ band, it is renormalized by the factor of 3, while DXZ DYZ is renormalized by the factor of 7. And therefore, as it is known, this spin orbit induced hybridization, it also renormalizes the same way. Of course, we can't say for sure whether it will renormalize by the smallest factor or by the largest factor. So the rough estimate for inverted gap in this case is something between these two values. So because in theory, it's predicted to be 15 millieV, maybe 18 millieV in some calculations, which means that the real size is expected at least 5 millieV, at least 2 millieV, and the largest possible size is 5 millieV. So it's quite big already, expected to be much bigger than in iron tolerant selenium. So it's already a good start. But another important factor is superconductivity, and this is the analogy that I was talking to you before. In this case, for LFS, it has TC of 18 Kelvin, and its superconducting gap is around 6 millieV. It's already was reported in literature. It also arose the same number from our experiments. This is laser ARPAs because we wanted to have the highest resolution possible. And from this comparison of data to, again, some DFT calculations, these ones, I think mouse is not working. This one is done by Klaus Kopernik. Previous one is done by Alexander Yeraсько. So this is the band structure integrated over the whole brilliant zone, and you can even see KZ broadening here because like different points, gamma point, Z point, so they all align here. And it's nice that on laser ARPAs we also see this KZ broadening here. So it's also quite unique result if you compare it to the literature. And it showed us that this Dirac point, which should be where the surface states arise, it's just slightly lower than the superconducting gap itself. This is non-superconducting state, superconducting state, because again, Tc for it is around 18 Kelvin. And that means that if we have inverted gap of that size and superconducting gap is so big, it means that it bends it farther away from the Fermi level, and it also squishes it. And to figure it out in more details what is happening, we tried to model it. I didn't put any formula here, but luckily previous speaker also mentioned it very nicely. RPS gives us essentially a spectral function, which is imaginary part of green function of quasi-particles interactions. And in that regard, it's easy just to write it analytically. And this is what has been done. So this spectra are analytical formulation of two bands, which are separated by 5 millieV. So in this case, we call it inverted gap. And superconductivity that we induce is 6 millieV by simple PCS model. And we consider three cases when upper band is above Fermi level, lower band is below Fermi level. Then it's the upper one touches the Fermi level, and the last case is when the upper band is slightly lower. And that's again the analogy I was given. If they are on the other sides, on the different sides from the Fermi level, we get the superconductivity tears it apart, and surface states are expected to be quite distinguished. Ideally, we want them to be, of course, so that the Dirac cone is exactly on the Fermi level. But if the moment the upper band touches the Fermi level, we get inverted gap, first of all, moved farther away from Fermi level. And secondly, it gets squished by superconductivity. So this is the case of superconductivity and topology basically competing. And this interplay plays an important role in this material. And in case when this band is even deeper, it gets even worse. Again, this is for the case of 5 millieV inverted gap. If the gap is smaller, the effect is even more, is even stronger. And that's why the ideal solution how to proceed with this is to dope the material with holes, which will move this up. So like this band should move higher, therefore inverted gap should move higher. And ideally we want, of course, this case, or at least this case. And this is what we have done. We've measured lithium iron arsenide doped with vanadium 1%, and in case of first of all, 1% vanadium doping decreases the superconducting temperature. So now it's not 18 Kelvin, now it's around 10 Kelvin, 10, 11. And therefore, superconducting gap naturally also decreases. So again, both from our measurements and from just because it changes linearly in this case, it corresponds nicely that the size of the superconducting gap is about 3.5 millieV, but at the same time, the Dirac point position, we see that it's around 4 millieV from careful data analysis, but there can be a bit more done with it. And this brings us closer, unfortunately, to this second case, which still is better than what we've had before. So this is to confirm whether there are surface states here. Ideally, STM should be done as well, but for now, this is the main result that we have, the understanding of what is happening with the inverted gap and how to realize topological surface states actually in this material. So to sum up, I think I'm already running out of time anyway. Interplay of superconductivity and topology in this material is very crucial, and I've tried to show you both by some model spectra and by real data. And for LiFAS, for pure LiFAS, it's very important to take into account the strong renormalization, which differs along different bands. For PZ, like I mentioned, it's 3.5. For TXZ, DYZ, it's closer to 7, so that brings the size of inverted gap between 2 and 5 millieV. And vanadium doping is the way that we expect to make LiFAS topological, but again, one needs to be careful because too much vanadium doping and it will be not superconducting anymore. So 1% at the moment looks like the ideal doping amount. Acknowledgements, this work has been done at IFW Dresden with Sergey Sharapov, with PhD students who were working, and still some of which are now working there as well. Sample growers, of course, people who helped us at Helmholtz Center in Berlin at BESI, Alexander Yaresko, who did the DFT calculations, and Alexander Kurdyuk for all the talks and discussions on this topic. So thank you for the attention. If you have any questions, I'll be glad to answer them.
Are there any questions? Yeah, where's the microphone?
Very nice talk and very nice work on the band structure. I just wanted to bring up a point of discussion that for the surface states or Majorana bound states or things like that, they're fragile to whatever's on the surface and disorder as well. So they, you might have the right band structure in average bulk, but they might still not be there, or there might be still other things, spurious states. And this is lessons from other systems that we're looking at, but I think it's a more general lesson than just for nanolayers or let's say.
Yes, thank you for the comment. That is very true. What is interesting also that from my experience, when we have something on this, like ARPAS is of course surface sensitive, obviously, but it's also then samples are being measured in ultra high vacuum, and we even saw on many samples how like the samples which are sensitive, not specifically topology, not specifically surface states, but in general, when it's sensitive, you see it during measurements. Like in 1 hour, you already see that the surface got worse if it's very sensitive. And in case of lithium iron arsenide, it's also true. So of course it's possible what you are saying, but we measured a lot of samples, and there were a lot of extra precautions, like not putting it into the air because lithium is reacting with air very strongly. We were seeing with LiFS also that the band structure was quite quickly deteriorating with time.
Anything else? If not, let's thank Volodymyr again. We're about 20 minutes late, but I guess there will be a 30-minute break, right? Or something. Yeah.
The next speaker now, the last section of the day is Sharapov. Go ahead.
Well, I would like to thank the organizers. Okay, fine. I would like to thank the organizers for making this beautiful event, and I'm impressed by a huge amount of our foreign colleagues who came to support us. So it's really a very big pleasure to see all of you, and all of you in Zoom and so many not in Zoom. So I would like to present the results that we started to work recently on the so-called rhombohedral graphene, and these results are obtained with Swiss colleagues Oleg Derzhko and Yaroslav Jumagulov, and also with Arsen Gerasimchuk, and I am going to present basically two works. The first one in PhysRev is completely theoretical, and what happened is that in Lausanne, next door to Oleg Derzhko, are sitting experimentalists who are doing experiments exactly with this system. So we were invited to try to explain these experimental results, and so I will probably mostly concentrate on theoretical part, but since I saw that this kind of graphene probably it looks like my talk is the only one, I will try to make some introduction to explain. So the outline of my talk is the following: that I will introduce this new well, it's not quite new, but I saw that in recent years experiment has making huge progress, and there are a lot of work for theoreticians to do. Then introduce effective low energy to band model, which is very good for analytic work. Explain model of interacting Hamiltonians that we use it in our approach, and discuss which kind of instabilities in this material we discovered, and the work done is rather large, so I will concentrate on examples of main result obtained in so-called random phase approximation and Parquet approximation, then explain what is non-volatile and hysteretic anomalous Hall effect, which is observed in this system. Introduce the simplest Landau model for free energy, which was used to explain this experiment, and present conclusion. So, what is this rhombohedral graphene? It is known that there are when we create graphite from graphene, there are many different ways to stack graphene planes. So most common is so-called Bernal stacking, which is known, for example, for bilayer graphene. And there is rhombohedral stacking where we have like shown in this picture, that B atom of second layer are just above A atom. Then next layer, the picture is again that A atom on top of B atom. And since we already shifted by one unit cell, hexagonal, then the picture repeats itself. And here are examples of band calculation for one K point. So first one, you see this is just monolayer graphene, bilayer graphene, and three-layer graphene, and so on. And these features which develop here, they are caused by so-called trigonal warping effects. It's rhombohedral graphene. The problem with the system, it's less stable and less common, and thermodynamically it's less stable. But still, it turned out that it's much simpler and easier for doing experimental and also theoretical work platform as compared to the twisted graphene, which you heard about. And the progress which was done in the experiment in the recent years, that we know that, for example, for monolayer graphene, it was since it was possible to observe it in optical microscope and then to do work. Here, more sophisticated experimental methods are necessary to recognize where we have this rhombohedral graphene. And then it's encapsulated in boron nitride, and huge experimental work is done. And what's theoretically funny about this system? Here is a dispersion law. It's just plus minus k in power n, where k is a wave vector and number of layers. And why it's interesting, you see that the next equation which I wrote is the density of states, and you see that at some number of layers, it has already the singularity. And for people who are doing superconductivity, and this is something like how to think about this dispersion, that those are approximately flat bands. And from our experience with superconductivity, we know that when the bands are flat, there is enhancement of density of states, and BCS equations shows rise of critical temperature. And this explains all business about flat bands. Those are very interesting system for realizing strongly correlated phenomena. And not only superconductivity. And what's interesting that in these experiments, basically, another tuning parameter is just the number of layers, and the experiments are actively done. Here I show experimental results of this group, just scanning tunneling spectroscopy done on multi-layer graphene. And you see the top figure is experimental one, and you see that this peak, central peak, is exactly this enhancement of the density of states. And here you see that 3-layer, 4-layer, and so on. And below are theoretical calculations, and the peaks are which are on left or on the right from the main peak. Those are contribution already from the higher bands, which is this stage I completely ignore. And what's interesting, this scanning tunneling spectroscopy shows that this central peak, when temperature is lowered, is divided by 2. So there is a sign of some gap opening, apparently. So this is exactly what we are looking for. So this is the reason why this monolayer graphene is so interesting. And here already I show this picture from experimental paper done with colleagues. So here is the system of, they studied 6-layer graphene. As usually people invent abbreviation, like I remember from high temperature superconductivity by BCO, ta-ta-ta. Here is R, rhombohedral, 6 number of layers, G is graphene. So new equation in these articles. And so this structure is encapsulated in hexagonal boron nitride, and done standard for graphene science double gate setup. So what does it mean? That we can tuning gate voltage on one gate and tuning voltage between the gates. We can tune the carrier density independently and electrostatic field perpendicular to the layers. So those are both tuning parameters. And here is already this color plot. So here the carrier density is changed, this N, and gate voltage, and you see this is the diagonal resistance of the sample. And the experimentalists this time concentrated on these areas of low carrier density, and inserts are already Hall conductivity measured. And you see already something interesting about, this is what I show, that those are measurements done in zero magnetic field. And apparently you see a sign of anomalous Hall effect. It's already interesting because it shows that there is spontaneous time reversal symmetry breaking in this system. This is the reason why it's interesting. And say in a few words, it's a kind of, for anomalous Hall effect, you usually dream to create quantum anomalous Hall effect for realizing Hall conductivity standards without magnetic fields. This is the kind of goal of playing with these materials. And as I say, that trigonal warping effects spoil system, and it's believed that compromise between when we have flat bands and it's not spoiled by trigonal warping effects, this is around n number of layers 5. And here I just show you two reference just to sort of justify that this talk really belongs to this workshop. The first one is paper from 2021 is superconductivity discovered in 3-layer graphene. Of course, critical temperature is not something impressive, but no one does not promise to make wires from the system. Another thing is layer title layer polarized ferromagnetism. And how theoreticians like to treat this model? In graphite science, there is well known from 1950s Slonchevsky-Weiss McClure model, where introduced nearest neighbor hopping in single layers, this gamma naught, gamma 0, then interlayer hopping vertical, and all bunch of possible hoppings. But in simply theoretical model, we just restrict by those two hoppings. So this is unit cell of n-layer graphene, neglect trigonal warping effect, and as a result obtain very simple effective Hamiltonian. you see that if you look at this is just by 2x2 matrix in pseudo-spin space. So for those, you see n equal to 1, this is monolayer graphene. N equal to 2, this is rather known case of bilayer graphene. Here, tau, by the way, is valley index because we always have two valleys. And the spinors describe A1, Bn means that quasi-particles are living in, for this is just the lowest band. The quasi-particles are living only on top layer and down layer, not inside the sample. And here is this Hamiltonian, which we worked for analytical calculation. So it's just 2x2 matrix. If also we add term which, what should I say, that in this language, this vertical electron field, I say the spectrum is k plus minus k in power n, but this vertical electron field also opens a gap additional in the spectrum already. So this is a controllable parameter, and another controllable parameter is chemical potential. And this is a picture of this band dispersion and why it's interesting for the flat bands. So which model for interaction we considered? This is so-called two-valley Coulomb interaction model. Technically, it's very simple. We have repulsion within each valley with the parameter V0, and we have repulsion between different valleys k plus, k minus. This is V1. And one would obviously expect that in practice V0 is larger than V1, but as theoreticians, we would like to play with the different options. For example, for single valley, it's SU2 by SU2. So one SU2 is responsible for spin, another SU2 for valleys symmetry. And if we have degeneracy point, V0 equal to V1, this is SU4 symmetry. And this interaction can be written as interaction in the density channel and interaction in the spin channel. And here introduced generalized label L is tau. This is valley degree of freedom, and sigma is real spin degree of freedom. And how we treat normal state instabilities. Let me again for theoreticians remind basic problem from Abrikosov-Rykov-Zelashinsky textbook that in superconductivity, you remember that we have interaction in Cooper channel and infinite set of diagrams, and which shows that electrons create Cooper pairs. This is when we consider normal state. And this is generalized susceptibility is calculated. And in our case, that in superconductivity, we restrict ourselves but by just superconductivity. But I should remind you that the situation in different channels of superconductivity can be also more tricky. S wave, D wave, P wave, and so on. Here we have all possible instabilities, including magnetic. So this generalized susceptibility is expressed by this equation, which in diagram language is written like this. So for he notice bare susceptibility, just bare bubble, call it bubble term, and F is full vertex. And in contrast to single particle quantities, two particle where reducible, irreducible diagrams have definite meaning for all cases. In two particle case, reducibility of the vertices depends also on specific channel we consider. So reducible, irreducible means that diagram is called irreducible if we cannot cut it into pieces, just cut in two lines. And it's reducible if we can do this. This is a reducible diagram in particle Hall channel. You see that one arrow in one direction, another arrow in the opposite, so this is a particle hole. And in this problem, another channel is vertical particle hole, so-called, and particle-particle. And I skip basically in my talk huge amount of technical details and just state that we calculated generalized susceptibility and channel irreducible vertices for each channel, and singularity of this susceptibility. This is a signal of instability. And it's exactly like in superconductivity, the susceptibility diverges. And we, in our work, we did both. Okay. So this is just to show bare susceptibility via analytical calculation is possible. Another one, I show instability. This is a magnetic instability, stoner instability, and superconducting instabilities. And examples of the main results that we calculated, for example, critical temperature as a function of number of layers. For example, this is the case of random phase approximation. We calculated phase diagram. An interesting feature is reentrant behavior. So we increase the temperature, and this intervallic, so-called coherence phase appears. And this is very interesting feature, reentrant behavior. We discovered that similar related work of Chubukov shows the same behavior. It's related to non-monoclonic dependence of bare susceptibility in this problem. So, and as I say, we did restricted model, but we also did calculation for the full model of, in this case, 3-layer graphene, and we showed that this reentrance behavior to related non-monotonic dependence of the susceptibility. Okay, so this is the results for Parquet approximation. It's basically the same, but in random phase approximation, we did not have superconducting instabilities. In Parquet approximation, they emerged in this problem. And I want to concentrate on this anomalous Hall effect in hysteretic behavior. So what does it mean? We have the Hall conductivity as a function of carrier density and gate voltage. So if I change, make sweep and carrier density, it switches to the opposite sign. Then if I come, then it switches, and to come back, I should do the switch in the opposite direction. And in the same feature appears in if I change gate for this electric field perpendicular to the plane. So again, this hysteretic behavior. And within our model, we derived, so we considered all possible interactions. We considered spin magnetization, orbital magnetization, and we derived Landau free energy. Not Landau-Ginzburg, I stress. Landau-Ginzburg is the kinetic term, we derived just Landau. And we know that in Landau theory of superconductivity, Landau-Ginzburg, there is no hysteretic behavior. Because it's or the parameter square or the parameter in power 4. In our case, because it's magnetic problem, it appears that there is a cubic term. And cubic term, so the main parameter which is responsible for this magnetization is orbital magnetization. And cubic term allows to, when we do sweeps, to the system firstly from one state goes to another stable, metastable state. And during the opposite sweep it switches back. So this is our interpretation of this experimental results. Okay, so those are my conclusions, that we identified a bunch of correlated phases and conditions under which they may emerge in random phase approximation and Parquet approximation for n-layer system by considering this two-band model. And when it was necessary, we also did calculation numerical for the full model to confirm of the features. We estimated critical temperatures for this phase transitions using both approximation and got some analytical results, which is for this kind of problems is quite tricky. The third result is experimental, so system behaves very unusually, so there is hysteretic behavior of the system, that the system can change sign of anomalous Hall magnetization during the sweeps of carrier density and electric, this is called a displacement field, perpendicular field to the planes. And this behavior we, I would say, quantitatively captured by Landau free energy model. But I should stress that for this model, all these coefficients are derived from the microscopical model, and for our consideration, it's non-trivial to take into account their dependence on the model parameters, on the displacement field, on the chemical potential, and so on. So thank you for attention.
Thank you for keeping the time. So questions? Yeah.
Thank you for a very clear talk. The correlated phases, can you say a bit more about them? Are they all gapped phases?
Okay, you see, we use it two approaches. The approach with this approximations. This is the approach to study normal state instability, so they don't have the gaps are not open. We are looking for critical temperature. This is one approach. So basically, the problem for this, in contrast to superconductivity, you know, you're looking for superconductivity, so you already forget everything. Here's the formulation of the problem to identify all possible kind of instabilities and to estimate which one is winning, which one has a higher temperature, basically. This is the idea. So when I picked up the results for this paper, I just showed you already instability, which we decided it's leading. So you see, in one approximation, it's this in intervallic phase. In Parquet approximations, it actually already stoner density channel which wins. And another approach with Landau effective model, we already took only 3 channels. We included this already gap parameters, but those are not gaps in the sense that those are magnetic instabilities. They are not modifying the gap, they go with the chemical potential. So this is the magnetism.
Any further questions? Yeah, that was a soon time. It has 6 minutes for questions.
I've tried.
Sergey, you have a question?
Just a minor question. So this 2-band model, it is specifically derived for this rhombohedral stacking, or?
The thing that only for rhombohedral stacking, we have this flat-like bands. For any other stacking does not produce such bands. So this model is designed exactly to treat them.
So I have a very short question.
The
phase transition.
A number of questions about the slides, but
which one?
For this and for the next one, we can discuss it later. So it is, you show one Diracon, and then some nodes appears here, right? They are how many? 3 or
3?
Or it is always 3, right?
No.
It depends on the number.
It depends on the number of layers. This is the effect of trigonal warping. So in the oversimplified, for example, bilayer graphene, oversimplified model, it just says it's 2 parabolical bands are touching. But if you include in the consideration, basically in this model, if you include trigonal warping terms, then you discover that instead of 2 paraboloids touching each other, there are bands with it's actually 4 actually.
Okay.
It's actually, if you look carefully, it's 4. It's 3 legs and the central one.
So this is, and put you on the next slide, just a short question about this. So you have this two sets of one-Fock singularities, right? It's above the Fermi level, below the Fermi level. No, not this, but before. So you should have these two peaks like this, splitted peaks. When we on this, above this experimental structure, this looks like it is just one of them is thin. It is not centered.
Okay, my belief that it's probably if you include disorder effects in something like this, you should really have very clean samples, probably very low temperatures to see this effect of these legs. They are kind of blurred. This is actually here the temperature is 77 Kelvin, so this is the answer.
I mean, why they are not symmetric? The question was, but okay.
Okay, probably okay, actually, I would say that I don't know precisely because I see that the band calculation produces symmetry. This is not what we did, but I see.
This I don't understand because it is one-Fock singularities below and above. Why
sorry, what do you mean below and above?
Before.
No. I believe that we just have. Sorry. I believe that we observe just this feature.
Here you have one-Fock singularity. Here one-Fock set of one-Fock.
But I believe that at 77 Kelvin you cannot you really need experiments on ultra clean samples. What I know for bilayer graphene, you need experiments on ultra clean samples at low temperatures to resolve these legs. This is the reason why oversimplified model which ignores this is used.
I have we have a question. No, I meant to short question for me, not for you. That's what. I have a short question, very short question. This Landau theory, you have a cubic term, you have a first order phase transition, right?
Yes.
Things like that.
Yes.
Okay, cool. You don't have a phase diagram there, right? It doesn't matter.
No. Those are the phase diagram.
Okay.
This is a theoretical calculation.
Okay, so thank you again.
Okay. Thank you.
So, next speaker is Oleg Derzhko.
I would like to thank the organizers for possibility to discuss our recent work, which concerns frustrated quantum spin systems. And frustrated quantum spin systems provided a lot of surprises. But in my today's talk, I wish to discuss one specific phenomena which, to my best knowledge, have been not noticed before. So usually we know that the properties of macroscopic body, like, for example, the specific heat per kilogram, do not depend on the form of the body. In my talk, I will illustrate that this may be not the case in the case of frustrated quantum magnets. So I will demonstrate that specific heat of some specific frustrated quantum magnets may be form dependent. And putting this statement in extremely sharp way, I may say that measuring the specific heat, we can establish the form of the body. So I have to start from, I don't know why it doesn't work. Okay, from thanks, of course, I have to thank the National Research Foundation of Ukraine. They gave us money for these studies, and probably even more importantly, I have to thank the armed forces of Ukraine for stopping Russians which wish to spread to the West and therefore we can do physics almost as usually. So here is the outline of my talk. Singlet state of spins 1/2 would play an important role in my talk. I will also show that many singlet states, which again are very important for the system which I intend to consider, may be counted using classical lattice gas model. And this way I will be able to construct the low temperature thermodynamics. And using some results from combinatorics, I will show that this low temperature thermodynamics may show the dependence of bulk properties on the form of the solid. In fact, my talk is based on one published paper, and one paper is still in preparation. So in my talk, I will consider ordinary Heisenberg model of spin 1/2, which are placed on some lattice and which interact between, and there is interaction, Heisenberg exchange interaction between neighboring sides. And in addition, I have also an external magnetic field. This interaction is antiferromagnetic. If you consider two spins 1/2, the eigenstates of this Hamiltonian is well known. You have four states, one of which is singlet, and three other states form a component of a triplet, and here is the energy of these states. Such states appear to be important for so-called bilayer lattices, and here I illustrate three of them. That is frustrated square bilayer, frustrated honeycomb bilayer, and here is frustrated triangular bilayer. These lattices where frustrated is important because there are some interaction between next nearest neighbor sites in the upper and lower layer. And the important condition for my talk would be the following relation between the parameters. So the interaction along all black lines is the same, and it can be called J, and it is antiferromagnetic. And interaction along red lines, that is intralayer interaction, should be sufficiently large, should exceed some critical value. For this special regime, parameter regime, I will show that some calculations can be done very accurately. So, okay. So frustrated quantum Heisenberg bilayers have several phases. So there are several perspectives, and each of which can be starting point for examination of their properties. So we can consider this system as a system with dispersionless or flat Magnon bands. We can also consider them as a system with local integrals of motion, and we can also start from the limit of non-interacting dimers and then treat interdimmer interaction perturbatively. Importantly, the states which are in some cases at low temperatures important for thermodynamics can be mapped onto classical hardcore objects, and therefore to find the properties of quantum system, we have to solve some counting problems of combinatorics. Equivalently, these problems can be rewritten as an Ising model in a longitudinal field, classical Ising model in longitudinal field, and this model provides an effective description of initial frustrated quantum Heisenberg bilayer. There are several solid-state realization of this theoretical model. In particular, this system presents the frustrated square lattice bilayer, and there are also frustrated honeycomb lattice bilayer as well as frustrated triangular lattice bilayer. But in my talk, I will speak about frustrated Kagome bilayer, and I will show that this case is different from the square, honeycomb, or triangular cases. Here is the lattice. You see two Kagome layers which are connected by strong interlayer interactions colored in red, and you have also frustration shown by blue and black lines, and the strength of this interaction will be the same. So here is, okay, the condition in which my consideration will be correct is J2 should be larger than 2J. As I told already, the one Magnon band spectrum consists of six branches, and the lowest one is completely flat. And you can calculate also the eigenstate which correspond to this flat band, and you will immediately recognize that these are singlets which are localized on red bonds from my previous transparency. This is, of course, correct when this red bond interaction is sufficiently strong. Then this lower flat band is really the lowest one. But we can obtain the same results using another perspective. So you can introduce such type of bond operators on J2 bond, that is the sum of two spin and the difference of two spin, and the Hamiltonian can be written in such a way. And if J1 equals Jx, you have this term drops out, and everything can be expressed in terms of these operators T. And obviously, T squares commute with the Hamiltonian, and that means that eigenstates can be labeled of Hamiltonian can be labeled by this local integral of motions, which can occur only two values, either 0 or 1. In the case of antiferromagnetic interaction between layer J2 is larger than 0, the low-lying state is, of course, when all T equals 0. That is clear from this Hamiltonian. But in the case of magnetic field, if I add here magnetic field, also spin polarized triplets will be important. That means that low-lying states have either T equals 0 or T equals 1, and that is the reason why this lattice gas description or classical description appear. So we can consider many singlet eigenstates. So there are three types of such many singlet states. The first type is when singlet which occupy, here I show only one layer and denote by colored dot the J2 bond which is occupied. And that means if neighboring bonds are not occupied, that would be a representation in terms of hard rhombi. And these states, which can be represented in terms of hard rhombi, have the following energy. And that is the number of this hard rhombi, and that is the energy of flat band. If you have two or more singlets, you may consider a rhombi which overlap. And in this case, you have to increase this energy by J for each overlap. And if you have 3 or more singlets, then you may have 3 overlaps, and each overlap again cost energy penalty J. So in this way, we can construct 2 to the power n over 2 states, and that is only a part of all states, 2 to the power of n. But I will show that these states dominate thermodynamics at low temperature under certain condition. And here, to check and to clarify this picture, we perform numerical calculations for 36 sites, that is exact generalization, and we perform also counting of the energy level degeneracy using hardcore rhombi representation. So we consider 2 types of lattice with different types of periodic boundary conditions. And in the subspace with a different value of Sz, we find the following energy. That is clear. The energy decreases by number 9. That is, for this particular case, is the saturation magnetic field. But what is more important, that is their degeneracy. So the degeneracy of the one spin flip state is 18, because there are 18 positions where it can occur. But if you have 2 spin flip, this number is 117. But if you have, for example, 6 spin flips, this number is 17. For other type of boundary conditions, you have the number which is shown here. So in fact, I analyzed the ground state in different energy in different subspace, and they are degeneracies. They are shown by red lines. And if you switch on magnetic field, you have to extract from each energy in these subspaces the Zeeman term, and therefore the picture in the presence of magnetic field close to this direction will look like this. So I can calculate this number counting the number of special configuration of hot dimmers on a Kagome, hot rhombi on a Kagome lattice, and I obtained the same number which I obtained from exact numerics for initial frustrated quantum bilayer. But using this effective using this hot core rhombi, I can consider a much larger system, and here I can show you the results. What is interesting that there are many full coverings, and the number of full coverings grows exponentially with system size. That is a peculiarity of the Kagome lattice, and here I show the number of full coverings. That means that there are no empty spaces in this Kagome lattice, which is covered by rhombi. And depending on the size of the lattice, the number of such coverings grows exponentially with the system size. That is not the case, for example, for square lattice, for which we have only two full coverings. You have either sublattice A is covered or sublattice B. For triangle lattice, you have free covering, but for the Kagome lattice, this nearest neighbor exclusion that is represented by rhombi allows many covering, and the number of this covering grows exponentially with time. And okay, I can, of course, this number of exponential, which grow exponentially with system size of coverings can be even estimated, because we have results for some finite systems, but we can extrapolate what happens in thermodynamic limited. We find this number, and this number is also known in combinatorics. So as I probably show already in my previous transparencies, instead of hot core rhombi, you can use hot dimmers on a honeycomb lattice. And there is one-to-one correspondence between hot core rhombi on a Kagome lattice and hot dimmers on a honeycomb lattice. And hot dimmers on a honeycomb lattice is a well-known problem in combinatorics. I mentioned here only a review paper on dimmers on two-dimensional lattice, but I will tend to this point in a few minutes. So now we can easily construct the thermodynamics. The contribution of localized eigenstate to thermodynamics is constructed in the following way. You have to consider a different number of hot dimmers, take to and multiply the Higgs exponent with the energy of this state by a degeneracy of this state. And if you make some manipulation, you obtain the function, the construction which is written in colored in green, and that is a grand canonical partition function of hot core rhombi on the Kagome lattice. And this function can be calculated using such lattice gas with the occupation number, or it can be calculated using simply Ising model, antiferromagnetic Ising model in a field, and the corresponding formula is written down here. So we can, as a result, we can calculate magnetization, susceptibility, entropy, specific heat using the representation of a contribution of this many singlet state in terms of classical lattice gas model. And now we have to compare our effective theory and exact results for frustrated Kagome lattice. Here is a magnetization curve, so our theory should be very good around the saturation field at low temperatures, when other states which are not described in terms of hot core rhombi do not come into play. And you see really that the results for of exact numerics shown by symbols, by circles, coincide perfectly with the analytical prediction from effective theory until the temperature is sufficiently low. Of course, we cannot reproduce high temperature peak of the specific heat as a function of temperature, because it is conditioned by other states which are not taken into account. And okay, here are also some results for other values of magnetic field when we deviate from the saturation. And again, at low temperature regime, we are able to reproduce exact results. And even in zero temperature, here is our result shown by red solid curve, which of course cannot reproduce high temperature peaks because a lot of states are beyond our description. But if we are in a strong magnetic field, all relevant states are taken into account. Well, I probably will skip this and come to the main dish. So, which I announced already. Do the bulk properties of the Kagome bilayer depend on its shape? These problems actually were put forward many years ago because the statistic of dimmers on lattice was discussed probably since half century or even more. But recently there is a very interesting paper where the same question was again put forward, and we can give affirmative answer to this question. Yes, they do depend. And here is my argument. There is a very nice mathematical paper by Elser, which was published in 1984. Elser considered hard dimmers on a honeycomb lattice of general hexagonal shape. Here I show a general hexagonal shape defined by three values, 4, 3, and 2. So these values K, L, and M enter this formula, and he found the number of coverings by hard dimmers of honeycomb lattice with arbitrary open boundary conditions defined by K, L, and M. And in thermodynamic limits, he found the following formula. So in thermodynamic limits, the log of this number of covering normalized by number of dimmers is actually the residual entropy, and the formula for this residual entropy is given in this line. And you can see that this residual entropy do depend on X, Y, and Z, and X, Y, and Z just determine the shape of this system. Now, here is this function which, okay, really depend on X, Y, and Z. And now I turn to the well-known formula for the specific heat. Specific heat divided by T and integrated from 0 to infinity should satisfy the sum rule. So it is log 2, I consider specific heat per site, minus ground state entropy, residual entropy. Usually it is 0, but in the system under consideration, it is not 0. And moreover, it depends on the shape of the system. That means that the specific heat should depend on the shape of the system. And that is, of course, for sure, because this sum rule and the statement of Elser concerning the value of this quantity in the right-hand side of equation immediately implies this dependence. So what would expect, I would expect from experimental measurement of specific heat. So you have consider such a system in the field just below the saturation, that is saturation field, just below the saturation, then you have to measure the temperature dependence of the specific heat. And there will be a low temperature peak and there will be a high temperature peak. Main maximum will remain unchanged, but this low temperature maximum should depend on the form of the sample. So how to check this? So that is unpublished already yet results. So numerics cannot be conclusive because it considers only 18 and 21 sites in this language of dimmers. Direct calculations are restricted to 50 sites, but Taras Krochmalski elaborated a transfer matrix calculation and he is able to obtain the results for thousands of sites. And then we can make extrapolation and predict what happens in the thermodynamic limit. So with this, I will summarize. So I'll discuss frustrated quantum antiferrometric Heisenberg bilayers, and there are localized eigenstates at certain parameter regime. They are low-lying states, and they dominate thermodynamics. And to calculate their contribution to thermodynamics, it is necessary to deal with classical statistics. And Kagome bilayer is very interesting because we face rhombi on a Kagome lattice or equivalently dimmers on a honeycomb lattice, and exponentially large degeneracy of the full covering immediately implies that there is no order disorder phase transition related to ordering of localized singlets, but instead you have a dependence of the bulk properties on the shape. And of course, we can elaborate the theory. I skip this around the flat bed limit, and the result you obtained XXZ model, classical again model on a Kagome lattice, pseudo-spin 1/2, and other bilayers also can be considered, but probably it is outside of the scope of my talk. So thank you for your attention.
Thank you very much for keeping the time. So, questions from the audience? What was this? Jurko, okay, come here, you or Jurko, doesn't matter.
I have a short question regarding interlayer coupling J2. You said that it should be larger than 2J.
Yes.
Why is it so?
Okay, this can be seen, for example, from this flat band, from this 1 Magnum spectra. So if it is, in order to have this band, the lowest one, you have to, here is a formula for the energy of these bands, and you can check, okay, here it is, when J1 equal Jx, and the flat band, it becomes the lowest one if J2 is larger than 2J. That is clear, that follows from this red line.
Yeah.
Probably there are some interesting results for other relations. So even in this numerics, we consider here J2 equals 5, J2 equals 3, J equals 2, that is marginal case. And you see that the degeneracy doesn't depend on J2, but here, or even for lower values, J2, other states become the lowest energy one, and physics is completely different.
Jurko.
Thank you. Thank you very much for the talk. Emma, it's not the question to you, but the question to the paper of 1984, where entropy depends on X, Y, and Z. And does it mean that when I go to the infinity, it will depend how I make my infinite object?
Well,
is such system ergodic?
Okay, so first I would like to say you that the formula which is shown here is just in the thermodynamic limit. So you consider K, L, and M large, but their ratio is X, Y, and Z. And if you go to the thermodynamic limit but preserve the form, the shape of your hexagon, so you obtain the same entropy. So you go, that is the result already for thermodynamic limit.
Yes. If I understand correctly, thermodynamic limit would mean K small, L small, and M small going to infinity, right?
Yes, K, L, M goes to infinity,
yeah,
but you keep the shape.
To formulate my question, would it depend how fast K, L, and M go to the infinity? I might put some additional laws of how do they increase.
Well, in fact, Elser obtained this formula for finite K, L, and M. And then he considered the limits, but I think that he introduced these variables X, Y, and Z, and they assume that they are finite. So I do not know details, actually. But he took this limit accurately.
Okay, can I just continue puzzled by that? That means that the state of your system is actually determined by the boundary, right?
Yes.
So it's kind of
yes, it's a very special regime.
Topology, one would say, it's a typical topological feature, right? Where the boundary determines the bulk of the system. Boundary
yes.
reflects the bulk.
Yes, yes, you may say in such a way, of course.
Get the mic to yes.
So two short questions. So is this Kagome kind of unique, or there can be other?
Yes, we could.
You said other bilayers. Yes?
Other bilayers. So we have considered actually frustrated bilayer. Yes, there is experimental realization of this Belay. J2 equals 110K, and all other interactions are 4 times smaller. And in this case, we predict there is something different. There we should be in this, instead of this time form-dependent low temperature peak, there should be Ising type of phase transition for square lattice. And in the case of triangle lattice, there should be a Potts type of phase transition.
It's, you know, this Kagome seems very special.
Kagome is very special.
But, like, is there any other lattice that is as special as Kagome?
Well, there are 11 Archimedean lattices, and probably the star lattice is similar to Kagome, yes.
Yeah, and the second question is there's this mapping onto these hardcore bosons or whatever, yeah, these dimers. So this mapping is basically, is it exact in some limit close to the saturation field, or it is not fully exact?
It is fully exact, but
in some parameters.
In principle, it is exact for any parameters, but these states are somewhere in the high energy part of the spectrum.
Okay, and then
therefore, they are not important, yes. These states are exact, but they are the low line only in the case when you have J2 and saturation around saturation field. Yeah. Only in this case, they are dominant for thermodynamics.
Thanks.
Other case, they are somewhere in the spectrum and we cannot see their effect.
Other questions from the audience online? Online? So if not, let's thank all of you online.
Thank you.
Thank you. Next speaker is Khristina Gnatenko. Yeah.
First of all, I would like to say many thanks to all the organizers of this days of celebration of science and here in this building of science. So I'm very also grateful for the possibility to share not just review on the quantum programming and the achievements of quantum programming, but also few words I will say about recent results, recent theoretical results, quantum information and development of quantum algorithmic results. So the title is Quantum Programming, and we will speak about current achievements, basis, properties of this programming, and also future prospects. I hope I will be very short. I understand that we have time restrictions. So the outline will be the following. First of all, I would like to present the basis of quantum information and quantum programming. I know that many of you know all these things, but just for introduction, for understanding other slides, I will present few important moments from quantum computing and quantum calculations. And I promised in the abstract that I will share with you the recent algorithms and also basic quantum algorithms, and I will explain that what does it mean that we have quantum supremacy. And then we will speak about fundamental studies in the field of quantum information, but also how to use quantum device in order to solve practical problems and when can we solve these problems. Of course, the last slide will be devoted to conclusions. Oh, sorry. It was not the right button. I stopped share instead of moving to another slide. Is it okay? Okay. It's very close to this. Okay. So in quantum computing, we speak about quantum bit, not classical bit, but quantum bit. And instead of values that we have in classical programming, I mean values 0 and 1, in quantum computing, we consider not just zeros and ones, but superposition of these values because of properties of quantum states. So in quantum computing, we have superposition of quantum states, and one quantum bit can be in state which is simultaneously 1 and 0 state. And the proportion can be arbitrary, so this constants, this C1 and C2 can be arbitrary constants. Of course, we have restriction because the normalization condition has to be satisfied. And also the total phase is not important in quantum states. We can speak this total phase, but we can achieve infinite number of different states just for one qubit. And in this point, it's very important to understand that if we have just one quantum bit, not one classical bit, but just one quantum bit, we can have infinite number of different states. And in these different states, we can write different quantum or classical information. So this is very important right now. If we consider many qubit states, for instance, 2-qubit state, we have superposition of 4 basis states. So you can see all these states in this slide. So we have 4 different constants, and in this step, we can also consider different encodings of information. So we can encode our classical or quantum information. We have to compute, we have to calculate in our quantum program. In this, for instance, basis states, 0, 0, it can be encoded one position of something or one information, and so on. This is known as basic encoding. If we encode information in these constants are complex values. So we have in the real parts of these complex values, we have amplitude encoding. If we encode information in phases, we have phase encoding. So even if we have one qubit, we have multiple number of ways how to write information we need to calculate or to analyze in quantum world. So the quantum programming is the art. As for me, it is the art how to combine different things, how to combine classical computing and quantum computing, how to map different properties from classical point of view and to the quantum point of view. In the case of n-qubit state, we have the sum of 2 to the power n quantum states. So we have a huge number of ways of encoding this information. And it is very important to understand that the largest IBM's quantum device, quantum processor, now it is more than 1,000 quantum bits. And in this case, we have 2 to the power 1,000, and this is huge, very huge amount. So we cannot simulate this quantum device with the help of any classical device established already. What about quantum computing? So in my slides, I have different protocols, and in these protocols, we use different gates. They are classical, some of them, but they are classical. We can find some representation, or we can achieve this action with the help of classical computing. For instance, it is NOT gate, controlled NOT gate. So NOT gate acts on the states 0s and 1s, and we obtain opposite states. From 0s we obtain 1, and from 1 we obtain 0. Controlled NOT gate is if operation in classical programming. So if quantum bit Q0 is in the state 1, we have action of this gate. If not, we do not have. So you can see from this slide the basic rules how we act with these classical gates, not controlled NOT gates on the states of quantum bits. But in quantum programming, we have gates. and operations that we cannot achieve in classical computing. So we can simulate them, but we need additional computational resources. We need additional classical bits. But we cannot achieve, for instance, Adamar action, Adamar gate operation in the case of one classical bit, classical device. This Adamar gate acts on the state 0 and 1, and we obtain superposition of zeros and ones, and we cannot achieve this in classical computing. Once more again, we have also rotations, and they are very important in quantum programming. So we can rotate the state of quantum bit. For instance, you can see here the Bloch sphere, and we can rotate the state of quantum bit in different directions around different axes, and we use this operator R, rotational operators. Then, what about quantum supremacy and basic quantum algorithms we study and already developed, and we studied these algorithms with students. So maybe to explain the quantum supremacy, the most common and most fascinating is for me is the problem of Bernstein-Vazirani. For instance, if you have the problem how to find unknown string or vector with unknown components, and you need to solve this problem with the help of, for instance, classical device and quantum device. So we can encode this unknown string, this vector S, in function. So we can construct function in the following way: as product of this vector and X vector, and then we can consider the problem, how to find all the components of this vector. It can be vector of different size. It can be vector of one component, two components, n components, and so on. So in the case of quantum computing, we can find all the components of vector of any dimension with the help of just one shot. Shot means that we run quantum protocol one time. This is fascinating because in the case of classical computing, to find all the components of vector, we have check. So I have to also to say that the components of vector S are zeros or ones, just zeros or ones. So we have to check each component. If the first component is 0, if the second component is 0 or 1, and so on. So we have to manipulate this function so many number of times as we have the dimension of this vector S. So this is known quantum algorithm Bernstein-Vazirani quantum algorithm already established. And the fascinating thing is here that at the end of this protocol, this is called quantum protocol, we obtain the result of measurement. So here we have measurement in standard basis. So we measure the projection of the state of each qubit to the z-axis. And the result of measurement will give us answer on all these components of this unknown vector. Why it is? Because it's quantum mechanics. Because the manipulation is presented here corresponds to the fact that at the end we will have not the superposition. We will have just one state which corresponds exactly to the state to the components of this unknown vector. It's fascinating as for me. And maybe for more detailed understanding of all these things, in the middle of this protocol we have quantum oracle, and this quantum oracle can be mapped. So it encodes this function. And how we can construct quantum oracle? So if we have a function for just one variable, we have to construct 2-qubit protocol, just 1 qubit to the variable function and of the we consider function and another qubit to the value of this function. And all these results can be read from the state of the last qubit. So if we have here 0, we have the result 0. If we have here 0, this corresponds to the variable we consider the function to the point we considered function. So and this is just control not operator is oracle for this function of one variable. Also, I would like to say that quantum supremacy means that we have possibility to obtain result faster with less resources with quantum computer than it can be in classical case. For instance, in the case of Bernstein-Bazirani algorithm, if we have string with one just single element, we have to compute function 1 time, and with classical computer and quantum computer, we have the same situation. But the difference is huge if we have 10 elements, arbitrary number of elements. So we have just one computation in the quantum case due to quantum mechanics, due to superposition, and due to that fact that in the quantum protocol constructed with Bernstein-Bazirani, we have reduction to the state of just one basis state corresponding to the unknown string. And what about maybe other algorithms already developed? I can say that we have different ways and different types of achievement quantum supremacy. Of course, it is just theoretically. And I present here just a few directions. So I have to say that optimization problems are fascinating, are very promising, and we can achieve fascinating results with them, with solving them with development of quantum devices. Also factorization, also study of properties of different systems, I mean different classical and quantum systems, also quantum machine learning. So the focus and the resource in these algorithms is of course supremacy, is of course superposition, sorry, but also internal quantum states. So due to superposition, we can calculate in parallel and we can achieve this more faster than it can be in classical case. What about just a few words about recent results in the field of quantum information obtained with my students. So we consider different spin systems with different interactions, but also different classical problems, different complex classical systems that can be mapped to these spin systems, namely that can be mapped to the quantum states. And for instance, I started with quantum graph states, but we also consider quantum network states, fractal quantum states, and so on. So if we have direct mapping of quantum object to the classical one, if it is this classical object is graph, we say that we have quantum graph state, and we consider different ways of construction of these quantum graph states. The recent result was devoted to the bipartite graphs. So this is the type of graphs in which we have two types of nodes constructed to with controlled NOT gates. And what is the core idea of these studies? The first part of the idea is the following. We need fundamental results. We need to study fundamental properties of the quantum states, for instance, the entailment of quantum states, because it is the source of quantum programming. But from the another point of view, we consider different ways how to find relation of these quantum properties with classical properties, and how to achieve quantum supremacy in solving, it's very strange, in solving different classical problems with quantum computing. And what we already obtained. So entailment was calculated for different multi-qubit quantum states. It was calculated analytically for general case of quantum states corresponding to arbitrary types of graphs, but also we calculate the entailment with quantum computing, with quantum programming. For instance, you can see this crosses corresponding to results of quantum computing and this plot, this surface corresponding to the analytical results. The result is already published. But what other achievements? So we also considered quantum correlators, and we found the interesting results that quantum correlators are related to the properties of graphs. For instance, the number of vertices with odd degrees, even degrees, but not just these properties, but also with the number of rectangles in graph, number of closed circuits in graph. For instance, in the case of tripartite graph, we obtained that quantum correlators. So this is just theoretical results, but very important that we have relation. We have a relation of these theoretical results with the classical. Yes, I see. With the classical properties. I do not know the reason why it is just not constant. Okay. I need just a few minutes to finish. It is just very short review of the results of studies of quantum states that can be represented with classical objects. They are graphs, networks, and so on. No, it's okay. I because I have just 2 minutes. I would like to focus on the future.
Well, let's do 3 minutes.
Okay. Okay. So first, I would like to highlight the examples of practical usages of graphs and these results related to the quantum graph properties. So with the help of already developed algorithms of studies of structural properties of graphs, we can solve practical problems in the field of resource allocation, in the field of matching problems. So networks we have also in medicine, networks we have in machine learning, and I'm also doing some research in quantum machine learning. But if it is not just in the field of graphs, in the field of classical objects that can be represented with networks, complex systems, I want to highlight the maybe possible prospects. We cannot say that we will achieve all this in 1 year, 5 years. We can achieve, I hope that we can achieve. So these scalable quantum processors, also applications of quantum computing in solving different practical problems in optimization, also machine learning, designing new materials. And I have to say that currently many algorithms already developed are not just quantum, they are both quantum and classical. what do I mean? That we have part of computing, we have to do it with the help of quantum processor, and another part, we have analyzed these results of quantum programming with the help of classical programming. So these algorithms are very promising. Also, I have to say that maybe in 10 years we will have possibilities to solve practical problems with quantum devices. What do I mean practical problems? Problems of optimization and cryptography, also in medicine and designing of different kinds of materials of different types, because quantum processors are natural resources and natural systems, quantum systems, and we can study different problems of quantum mechanics just considering quantum system. So currently I feel myself not just as theoretical physicist, but also a little bit experimentalist because of running the quantum protocols on real quantum device. Of course, in this short presentation, I didn't explain all the details of quantum programming and all these future perspectives, but I hope that maybe a few slides were interesting for you and well understood. So thank you once more again for the possibility of being here and presenting these results. Thank you for your attention. Thank you.
And thanks. We have time for questions. Any questions?
Yeah, I understand. I do not understand it, but I mean, just in condensed matter, some prospects. How do you think in terms of number of qubit which would be needed? For example, solving the Hubbard model with how many sides, or some minimum in multidimensional parameter space with n parameters. So could you say how many qubits we need for such a to be effective?
Yes. So if you would like to model spin 1/2 systems, so you need 1 qubit for 1 spin. If you have to model a 1 spin system, you have to use 2 qubits for 1 spin. So it's scalable, and the open question how to solve all these problems from the condensed matter field. So how to not just solve but achieve quantum supremacy, because we don't need just to compute things we can compute classically with quantum programming. We focus on fields that are interested in from the point of view that we can achieve something faster with quantum computing than in classical case. So in condensed matter physics, this can be done with quantum programming. So algorithms already developed how to construct and calculate the statistical properties, but scientists did not achieve quantum supremacy in this field and didn't calculate the properties of huge systems because of the noisy quantum devices. So we cannot achieve correct results because of quantum errors.
There is one more question by Volodymyr.
Yes, thank you for your talk. I have a question. At the beginning, you said that 1 qubit already covers like infinite number of states, essentially. But it still is being used in pair with standard classical computers, usually. And that's my question. Is it always the case, and that's the roadmap, that it's planned to be like quantum computing, which has these infinite states, but then it collapses to some, like, with some discretization, you get one of the numbers, and then that is getting to the classical computer? Or are there some ideas and prototypes of doing it completely analogous, for example, and whether there is sense to it? So how does this look like at the moment?
Okay, if I understand the question correctly, if not, please roomy. So we can simulate the quantum computing with the help of classical bits. So we can do everything as we did in quantum case with the help of classical computer. But for this case, we need exponential growing of the number of classical bits. So to simulate just one qubit protocol, we need 2 classical bits. But what I mean if I consider infinite number of states, so because of this superposition, if I encode my information not just in basic encoding, but in amplitude encoding or phase encoding, so I can encode here different values. This means that we have huge difference between quantum world and classical.
Okay,
Yeah, thank you.
okay, thank you. So I think I will close the session.
So the next event is conference dinner, and I think you all should know where to go, right?